All right, thanks again, and welcome to today's webinar. It's about robotics and low latency and how transport protocols can affect the performance of robotic systems in industrial environments. My name is Andrew Heimerman, and I'm the lead solutions engineer at Stacks. Yes, so let's get started. So I'm sure many of you know, if you're in the robotics industry, that robots are struggling currently with connectivity. But as we move towards more autonomous robotics, things that are controlled remotely from control centers in the cloud, low latency is critical for Industry 4.0 applications to really actually make them viable for industry. Like we could think of many examples, but let's say for safety of workers in the plant floor, autonomous robots need to be able to react quickly and in time, and also inform other robots of situations in their environment where latency could be the difference between catastrophic failure or an injury or worse, and a safe shutdown. So obviously this idea of connectivity doesn't just mean, okay, can I connect to the internet, but how quickly can I get a message across? And so that's what I want to focus on today. So if we look at the average response time between humans and robots, we see there's a huge difference between the two. So for humans, its average is about 220 milliseconds. And with current new robotic systems, the actuators and motors, you can actually get a response time of less than 2 milliseconds in certain cases. So what does this mean? That means that processes that happen with robots can go much faster. It means that shutting them down or making sure that tasks are performed properly is really then just dependent on how the control system is connected to the robot, namely the latency of the network. And industrial networking needs to support these higher throughput applications. But the current state, it's improving, obviously. So we'll go through the first things. Upgrades are being made, obviously, to industrial networks to use infrastructure that's based on 5G. So that means that we're increasing the bandwidth and more devices are being connected. So this is all really positive developments in the space. And obviously, this is going to keep growing. However, there are still many legacy systems or factories that haven't fully upgraded where it's still slower connections. Wireless connectivity also, even if it's 5G, can still be a little bit shoddy in these factories. And obviously, as you connect more machines, it means more data, which means there are network backups. Maybe there's just not enough infrastructure to handle how much data is trying to be pushed through the network. And the more infrastructure pieces like routers, switches, even leads to higher latency. So imagine you had a control system that's in the cloud and it has to go through a couple different routers and a switch, and just to get to the robot that's on the floor. That already adds in a significant amount of latency between what the control is that's being sent and the actual end result that's happening then on the factory floor. And lastly, many companies still rely on TCP only, which is where I'll go to a little bit later and why that can also maybe cause problems for latency. But first, before we do that, what are the main differences between TCP and UDP? So TCP, or the Transmission Control Protocol, is a connection-oriented protocol designed to create channels between different devices for sharing data packets. This means that it creates kind of a two-way highway between two different devices and ensures that all the information is relayed in the proper manner, so the proper order. If something gets lost in transit, it retransmits it. So you can ensure that you are going to get the data to the other machine that in a safe way from a network perspective. UDP, on the other hand, or user datagram protocol, is a connectionless protocol, which means that it just simply fires into a direction. So you tell it, okay, I want to send it to this endpoint, and whether or not the data gets there or not is irrelevant. So you can see that there are major differences between the principles of what these protocols do, and this actually can lead to differences in latency. And this brings me to my next point. TCP isn't optimized for real-time robotics. So if we look at how TCP actually works, kind of like I described before, you have to send multiple different packets or messages to to the other, from the client to the server or whatever, two machines, in order to establish a secure connection. So in this case, it takes 3 different packets to actually establish a connection through which data can be sent. Now, this happens not only just at the beginning, but let's say that you lose packets. So as I mentioned before, in industrial systems or industrial settings, wireless connections can be a little bit shoddy, especially with 5G. There's a lot of things like metal or even water droplets that can infect the actual the reception of the radio message, and that actually causes then TCP to break down. And then you have to keep on resending these acknowledgement or these synchronizing or acknowledgement messages, which means that you start cluttering up the network and it actually slowing down and increasing the latency between your 2 devices. And yeah, so for the first thing I just mentioned, and yes, exactly. So a shaky connection doesn't work well with TCP. Because TCP performs significantly worse with drop packets, which can be from congestion or misalignment in the network. So that somehow the alignment of the packet isn't coming in right, and you can't read the data properly, and then the packet's lost, or TCP thinks that it's lost. And what that actually causes TCP to do is what it was built when it was built in I don't know, 40 years ago. It was designed in order to handle really low throughput networks and to be able to control the congestion that goes through. So essentially when a shaky connection happens, TCP basically says, oh, okay, we don't have enough throughput, and we're gonna basically stop anybody else from sending through their messages until we figure out what's going on and throttle everybody else. So this congestion control mechanism is not optimized. And especially with 5G, even though the bandwidth is very high, the more machines that are trying to send data through, it still can cause a congestion at the other end. And a lot of implementations of TCP on specifically older machines is not optimized for for high bandwidth networks. And so it actually ends up kind of causing TCP to throttle itself and slow it down and cause more latency. So that's why TCP is not ideal for robotic situations, and how that even just like a protocol like this can affect your latency in an industrial setting. So the question is UDP the answer? So with UDP, latency is obviously reduced since you're only sending one message out. And you don't require some complex handshake. It obviously reduces the number of packets in the network, which means that you have less of a chance of getting this kind of bottleneck thing that happens with TCP. And lost packets don't affect the rest of the network's performance. So the messages, if they get lost or they get dropped or whatever happens to them, other applications can still keep on sending UDP through. So in the case, if we think about robotics, you have maybe streams of data coming from different machines or different robots, and you're just trying to push it out to some type of data service. Maybe it's telemetry data, for example. And you don't really care about maybe missing one data point or something like this. In this case, then you can be assured that through UDP, you're pushing through these packets without causing some type of a dam, preventing these other telemetric data from going through. Additionally, there's less overhead per packet. So UDP actually only uses 8 bytes versus 20 to 60 bytes for TCP. Even just the amount of data that goes through can cause issues for the bandwidth. So obviously, if you have a certain amount of bandwidth, you have TCP that's taking up more data per message. You would be able to fit more UDP packets through in the same amount of space. Additionally, another benefit for robotics and mobile things where they're trying to switch networks very often because of different Wi-Fi networks or different cell towers, there's no need to reestablish connections. So it means you can actually do mobile roaming since it's a fire and forget type of protocol. It also, through some like UDP hole punching, allows for NAT traversal, which helps you in when you're trying to get through different types of networks. But we don't have to go there today. That's a little bit more complicated. And then the other advantage is that there's no suboptimal congestion control. And I put the asterisk here because obviously this can go 2 ways. If you don't have a congestion control, you don't know if you're missing packets or you don't know what's going on necessarily with the network. But in this case, the problem with TCP was that the congestion control was actually causing more issues. So it can be an advantage also for UDP to not have that. Some of the disadvantages would be that there is no congestion control, like I just mentioned. And packet drops can cause issues if not dealt with. There's no acknowledgements of the received data. There could be incorrect packet ordering. So you don't know what's going on in the network. So you never know if you need someone to come in a certain time order, if that's going to actually happen. And then the last point is that UDP can be blocked by IT security. And this is problematic more in industry, I guess, than other fields. But it's from, I guess, a longstanding tradition of just using TCP for security reasons. So why did we choose why did we at Stacks choose UDP instead of TCP? Because we can fix and optimize all those problems that I just mentioned ourselves. So what we did is we implemented an optimal congestion control for our peer-to-peer system, which means that we can actually handle high throughput and high bandwidth networks, as well as deal with the loss of packets and deal with those and not cause the issues that TCP has, where we would create accidental blockages or backlogs of packets that aren't getting sent through. We also then created a lightweight acknowledgement and retransmission system. And something I didn't mention before, but TCP doesn't include encryption out of the box, which means you actually have to add even more messages in order to encrypt, such as with TLS. And with our protocol, we decided that we would be able to, or we created a method to actually encrypt the first message with the data and send it to the second machine without having to waste packets on establishing the certificates between the different devices. So actually, at the end of the day, we really have reduced what could be very complex. To go back to the TCP, what could be very complex is even if we added more transfers of data for the encryption and other things, we were able to reduce it then to only two messages, so the data and the acknowledgement when you're sending it out over our network. And this is all because we are able to use UDP. So we can also go through the numbers here just to show a little bit of comparison about how the protocol throughput is. As you can see, native TCP, the overhead is only 66 bytes, and the ACK is also 66 bytes. With our protocol, we were able to provide similar features to TCP, such as ordering and acknowledgement of the packet being received, as well as some congestion control. And we actually were able to reduce the message overhead by a little bit. And with negligible increase in the baseline of the message size, we're able to do all of those fancy things that TCP does, except with faster speeds, which you'll see here in a second. Oh, you can also compare then to other solutions such as VPNs, were significantly less in size. So, for example, then when we implemented our traffic control comparison, like I mentioned earlier, TCP, a lot of older systems are implementing suboptimal algorithms to control the traffic, and you can actually see that right here. So as we increase packet loss, we're actually increasing significantly in the TCP world. So packet loss, remember, can be anything from packets from delays because of switches or something like this, a lot of congestion in the network from other devices. So if a lot of robots are communicating at the same time, that can also cause packet loss. So it's not just they disappeared, but that it can be backed up and artificially created. So you can see that 44 seconds it takes to download a 3 megabyte file versus 6 seconds with our protocol. Now, as we reduce the bandwidth, these times get slightly closer, but you can still see that we're consistently above the benchmarks from TCP. And then even at really, really slow speeds and high packet loss, we are very close to what TCP already offers. And ideally, this is a very, would hopefully not be a realistic scenario. So that's all I have for you today. Just wanted to show you a little bit about how the protocols can actually affect the latency and data throughput in systems, and how robotic systems that need high throughput and low latency can think about how their what protocol they're using to actually communicate on to help reduce it in their industrial systems. So now I would love to open it up for a discussion. If there are any questions or if I can expand on anything, now is the time. Okay, I see your question, Christian. I do not believe we did with SMP v3. I can find out though and let you know. Any other questions that I can answer?
Andrew, thank you so much. I also have a question because I guess for robotic systems, the operating system, ROS 1 and 2 are very common to solve already lots of issues. Maybe you can also. I would be wondering what do they use, just to kind of see also. Thank you.
So I have a slide here, I believe. So there's a couple of different things that differ between both ROS 1 and ROS 2, both which cause connectivity issues, but kind of different ways. So ROS 1, which is probably the most prevalent in the industry just because it's older, uses a master worker setup, which can cause latency issues because you have a bottleneck basically through the control, which would be the master, and then the worker nodes. So that would be kind of a bottleneck there. It also uses TCP. I believe there is also a UDP version of their communications protocol, but I'm pretty sure that the standard is usually TCP. So it doesn't really support real-time operations. ROS 2 attempts to solve this issue with DDS, but it still kind of remains centralized since you have to have MQTT servers that are brokering the messages. And I mean, the DDS implementation also matters. Although there are some that are moving towards UDP, which is a good thing, because they're also trying to solve the same issues that I was just mentioning before with TCP. You can essentially get some of the same guarantees with TCP with UDP, like I mentioned. So there are some implementations of DDS that do that.
Okay, thank you so much. I would also wonder, because you mentioned on one of the slides about the hole punching, maybe you can cover a little bit from your perspective. Why this, can be interesting, and maybe everything that,
Yeah, exactly. So I don't have a slide for it, so I'll explain it from just voice. So why UDP hole punching is very interesting is it is a very lightweight way of getting a two-way connection to your devices between, like, let's say a cloud service and a device that's located in the field behind some like NAT or firewall. And it differs than VPNs, for example, because VPNs require like a setup and a lot of management, and they don't really scale out well. And same with reverse SSH, each application has to be individually configured to be able to communicate with the outside world. So, or to like link to the cloud. With UDP hole punching, it's interesting because all you need is one, let's say, outbound connection to your cloud service, and then you can establish a two-way connection over any type of network barrier. And where this gets even more interesting is you can then multiplex all of the applications. So this is what we are kind of doing with our protocol is you're able to take many applications that may be running on a robot, multiplex them, send them over UDP out to the cloud, and the cloud can then also then respond back to any of those applications through only one port. So it actually eliminates the need for any VPN setups, VPN management, or any SSH. So that's why I think it's a pretty interesting feature.
Got it. Thank you.
Are there any other questions? Otherwise, I thank everybody for coming. And obviously, if you want to reach out, my email is right here. If you have any questions that you think of later. And yes, I hope you all have a great rest of your afternoon, and looking forward to, oh yes, before I forget, we'll be having another webinar in a few weeks, and I will send out the information in the coming days. So stay tuned for that, and I hope to see you also there. So once again, thank you, and have a great rest of your day.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.